Yes. So once again, let us start with an elementary problem. Let's start with the elementary problem. First, just like every time, we just do a small elementary problem. So here is what the problem is about. We want to prove that for any n integer, obviously any natural number greater than or equal to 0, there is a polynomial. Obviously, this is complex numbers. See, there is a polynomial denoted by t and x. This is actually a very useful polynomial in a lot of places. But for the time being, we'll just t and x with with integer coefficients. With integer coefficients such that we have the following: 2 cosine of nz. Okay, 2 cosine of nz is the output when you input 2 cos z in the polynomial. Yeah, we want to just show that such a polynomial will exist. Yeah, let's think about this. Later on, this will be a useful polynomial, even in interpolations, polynomials, and so on. But for now, let us think. So when you input 2 cos x, 2 cos z, then the output turns out to be 2 cos nz. So it's an interesting polynomial. T1, right? So what would T1 be? 1. Why 1? So okay, let's see. So T1 of 2 cos z. I mean, yeah. So what do you think? Yeah. No, but it's right. I mean, in some sense, this is the identity polynomial. Yes. So this is T1. So T1x is x. Simple. Let's see what else can we say. And also we need integer coefficients. For 0, should it be 2? That's right. Yeah, for 0 you can take 2 if you want. I think, yeah. Yeah. You could take several things at 0. But yeah, 2 as a constant polynomial works. You could take x also, right? That would also work. No, so I was thinking that if you take this to be x, then t0 to oh no, wait. So we are no, sorry, yeah, you are absolutely right. You cannot take it to be x. That was yes, it has to be the constant polynomial so that for any cos z, absolutely. Yeah. Yes, that seems to be the right thing. So Tn has degree n. Yeah, that should be the case, I think. We don't have to prove the claim, but seems to be. So how do we go forward about T2 and so on? Yes, that's right. So that is something like what we should do, right? I think. So we have 2 cos square z minus 1. So then you know that you should be taking, so obviously, that's right. So then what should T2x be then? X square minus 1, right? Yeah, but then how do we prove for T3, T4, and so on? Huh. That will be easy for a power of 2, but can we say something more directly? So let us just assume that Tn exists for all n from yes, that's right. That can be done, but it will not lead to any insight, I think, into how we can do for okay. Okay. Yes, that's right. If you can do for 3x, if you can get, so what will it be? What will it be? Can we write it? Hmm. In any case, something will come, something simple. Yes, that's right. So then, no. But then if you know for 3x, then does that help you to know for 9x? Can you use 3x to write 9x? Let's say this exists. how could you use that? It will be a little complicated. Yeah, yeah. Hmm. Yes. 3x. Yeah. Yes, that is right. No, but the no, no, no. So that is right, but how is the 9x? How is the 3x helping? How is this helping us to do this? Like how do we use the existence for 3 for T3 to do T9? Right. That is really the question. And I think yes, yes, no. So that's exactly, yeah, that's right. That's right. That's exactly correct. Because if you have 9x, then you have written it like this, and then you know that for this you have a polynomial. But the only point is that in general, you will not know if it will have integer coefficients, right? So my point is that let's say you have proved for 3 to the power nx, right? Now, when you're going for 3 to the power n plus 1x, then then yeah, but the only problem is that you do not know if it will still be an integer coefficient polynomial. That you have to still reason out. That is not clear. Okay, but let's see. So this, if I write a 4, no, but one has to say if I write a 4 and then write a 3. No, no. So how do you know that there is a integer coefficient polynomial for this? It's not at all clear. Because, right, because no, we don't know, because you see this, for this we have a polynomial. So here it will be 2 times, if we remove this, here it will be t of 3 to the power n x, but the problem, it will be by 2. And then how do you know that in the end this will be integer coefficient? One has to prove that. It's not very clear that this will have integer coefficients, right? But it will have, I think, because the way we are, because there is a unique polynomial, obviously. There is a unique polynomial, right? Should be unique. We do have enough values. Yeah, so, but it's not clear from here. And also this is just for powers of 3s and powers of 2s. Yeah. But I think we can just think along the lines of induction itself, as you have done, and we can try to do the problem. For prime numbers, how would you prove for prime numbers? I don't think that will be any easier. Right. So, but I think yes, if we assume this till n naught, then we can simply go for, like, if you want to write this nz, right? And then we can just do this. No, this is nz cos a cos b minus sine a sine b, right? Now you see how do you do it? we can take we can assume a stronger statement. What should we assume so that we can use the induction? So induction will tell you that this has a polynomial for it, right? But number one, what is the polynomial for the other things? For the 2 sine and z sine z. Let's see. So by induction, we can actually assume that there is an Sn also, right? We can make the stronger assumption, right? Sn, so you can understand what Sn would be. Sn would be 2 sine. This is a very interesting way to do this. Like usually the stronger assumption you make will actually help you. So Sn exists for all, like this, right? So so maybe yeah, I should put n naught plus 1, right? So then you know that, then what do you know? Right. So then you know that there is a polynomial for this and for this. So then we can, how do we combine it? Let's see. Yeah. I think it's simple. So just want to think about it. So it is simply just induction. It's simply just we use the assumption, right? Right. So this will just be Tn 2 cos z, and then there is a cos z again, minus Sn 2 sine z, and there is a sine z again. But wait, we are not done, right? Hold on. Hold on. So what should be the polynomial? X. No, there seems to be something wrong, right? Because if you are going to put 2 cos z, but then here you are needing to put sine z, that is a problem. So this is not done, right? This approach is not, basically, you see, what we need to do is we need to write everything in terms of cos, in terms of 2 cos z, right? Then only we can say that this is a polynomial, this is some polynomial evaluated at 2 cos z. But here we have the sines. So so I do not know how to do this by this inductive approach, right? So let us actually try to use complex numbers then. I think this will work. I'm just maybe missing something, or maybe I do not know. The way I think this can be done is by using complex numbers, which is why we are doing this thing. Okay, so let's go there and see if we can do it via that. Otherwise, we'll think more about this after the class. So the complex number approach is basically simply as you can understand, we're trying to write cos nz in terms of powers of cos z in a systematic way. We know that this can be done, right? We know that you can eventually break it down, but we want to say that you will not need sines. You can write everything in terms of cosines in the end of the day. That's what we want to show, right? And yes, that is basically what we want to show. Okay, yes. So I think even here we could have made a stronger claim that this polynomial, that for this there is a polynomial which is in terms of cos or something like that. We could have done something like that. I think that would work. So I think it is something like this. We can say that for 2 sine nz, we can make this claim. There exists a polynomial Sn such that this is equal to sine z times Sn 2 cos z. You could have made a claim like this, and you can already see, right? If you, for example, if you take sine 3x, if you expand it, you can actually write it in terms of cos and using only one more sign, right? Because even if we take the initial expansion, so I think it is 4 sine cube z minus, or is it, it is something like that, right? Just something like that, yeah, like this. But then you see, you can just take out one of the signs, and then you have a sine squared minus this you can write in terms of cosines. You see, so so you have to, what we did wrong was we made this assumption, and this is actually not even correct. So if you do take small cases, you'll know, right? Even if you take sine 2z, you can understand. So this can actually be written as, no, so I mean the right hand side can actually be written as 2 cos z times, yeah, 2 cos z times the sine. Just you will need one more sine z. Everything else can be written as a polynomial of 2 cos z. So something like this you would have to do, um, to make. I think this will work. This does work already. Okay, but still, let's go and try to do this by complex numbers, and we see that we actually get more. We actually can see explicitly what that polynomial is. I think, as you were saying, binomial coefficients come up, so that was your intuition, and that we'll see is actually correct. uh, so, but through the recurrence is not so clear, maybe. So let's try to see that. So any ideas how we could use complex numbers in this kind of question? Yes, absolutely right. We want to use the De Moivre's theorem. So yeah, but how? How do we use? That's right. This is the statement, right? How do we use it? Yes, eventually we want to write cos nz only in terms of cos z. That is our eventual. We want an expansion which only uses cos z. And this was also one of the stems questions had used this idea in a limit problem. I remember. But in any case, that's small. So first of all, we have to get the cos nz in the picture, right? So first of all, let's try to get cos nz in the picture. So for that, we raise this to the power n. Right? We raise it to the power n because this is how you will get cos nz in the picture. So this side. But now you want an expansion of cos nz, or rather 2 cos nz, but you want an expansion of cos nz only in terms of cos, or Yeah, or at least you do not want the n in the argument, right? So then it's a very simple idea that you just want to expand this using the binomial theorem. Yeah, this part. Yeah, and we don't need much trigonometric identities. Maybe in the end you will need the cos square plus sine square is 1. Yeah, other than that, you just apply the binomial, right? No. We just expand this by the binomial, I think. We do not, all that is already encoded in the in theorem, right? In the De Moivre's theorem. So it's very simple now. I mean, it's just like this cos n minus 1, and but then this will have the I. So see, we just need the real part. So let's just expand the real part only. Okay. So you see, it's already clear that you can get rid of all the signs. As you can see, this is sine square. Yes, but we don't need that I, we just need the real part, right? So we will just expand, yeah. So then everything just falls in place, right? So just this, that's right. That's right, you see. So this is what it is about. It's very simple because now, but let us just try to work this out, work out the details. Yes, so in things like these, now let me do one thing. Let me write one more term because we need sine 2 cos. We need to write it as a polynomial in 2 cos z. So we have to be a little careful. So let us just do it and choose it. 1 minute. Oh yeah. So we have n minus 6. Yeah, I'll just write these many terms. Now this will be 6. Yeah. What else do we need to do? See, we need to write this as a polynomial. So we have a 2. So we'll use the 2. So multiply everything with 2. Now we need to write this as a polynomial in 2 cos z, not in cos z. So how do we do that? That seems, but no, yeah, but then we won't have integer coefficients. That is the problem, right? So if you write 2 cos nz and then you have to get 2 to the power n. Yeah, this integer coefficient thing is what is. Hmm. Yeah, that this divides 2 to the power n. Yeah, this is a little problematic. How do you show that it has integer coefficients? And it is also just n choose 0. It's not even that we can use. So this is where I'm getting stuck a little bit. Let's just think. 2 to the power n. So here we will need 2 to the power n minus 2. So we'll need to multiply divide by 2 to the power n minus 3 at least. How do you absorb those things? That seems impossible to absorb. 1 minute. Yeah, that seems. That's right. At least with this. Wait, are we making a mistake? 1 minute. If you Yes, the sign is here, but what does that do? Eventually, we want it as a polynomial and only cos. 1 minute. So, uh, yes. I understand that. This is, yeah, exactly. So that's what we will do. Okay. So after that, right? Uh, no. You're right. So after that, it becomes, yes, because from all these, from here you will get a cos to the power nz, right? If you so let's do that, and something like this. Yes, it will work out, but we don't have a good way to explain it yet. That is, yeah. So we have a 2 here, and here we have this, and here it's 1 minus cos square, right? And yeah, you see, so this will be n choose 2. So the n choose 2 will go. So you'll have cos z to the power n, and here from here you will get, no, not all of them, but you will have n choose 2, n choose 4, n choose 6, and so on. Yeah, and that will take care of this. And but how do you, but we have to, but it will get messy to explain, right? That is the thing for the later. So then you have to think of a slightly different way. 1 minute, 1 minute. So there will be a way. So this two cos z should remind us of something. We can, I think, directly do this like this, you see. Why? No. But how do we prove? Yes, but no. But this is not a polynomial in cos yet. It has sign also. It has signs also. Right. You want to show that when you get rid of all the signs and write everything in terms of 2 cos, it should be a I mean, it's not clear. This seems to have integer coefficients, but when you write it in terms of 2, everything only in terms of 2 cos z, then it may not have. A priori, we need to show that it will not have, right? That is the problem. Yes. Yeah. So that is the thing, but it's becoming a little messy to explain that, because for cos z to the power n, we are able to explain, but then similarly, you'll have to prove a lot of other identity. The sign, because sine 6z, when you write in terms of cos, it becomes messy, right? We don't have a clear explanation. But you see, this 2 cos z should, yeah, that's right. That's right. That's why, to get rid of that, we can do the following. We can just take the 2 cos z, for example, and this 2 cos z should actually have reminded us of something. So if you can use this notation, but if you call this x for a second, e to the power I z equal to x, then this is actually x plus 1 by x, right? Is that, yes. So if you, let's try to understand that. So if you, instead of each, I mean, you can use that language, but if you just use this, if you just call this, if you call this cos z plus I sin z equal to x, right? Then this 2 cos z becomes x plus 1 by x. Yeah, because you see x is equal, That's right. Yeah, that's right. And this is a very standard thing, right? Now, how can we use this? Can you think of a way to use this? Sorry. Yes. Yes. That's right. So this will be x to the power. Yes. This seems to fit. Yes, yes, this seems to fit better because it's already the 2 cos z is already there. Yeah. So yeah, yeah, it's using integer coefficients, right? That is a problem. Yes, that's why this seems better, right? So I think we can just proceed by raising this to the power n, because how else are you going to get the x to the power n, right? So you raise this to the power n, and then yes, yes. So we have the yes. So plus what? Plus that's plus n choose. Wait. And choose one. Okay, and choose one. Yeah, yes. So yes, it will be minus two. Right. And so let me write this a little on this side. Yeah, so this is a not so trivial problem. Seems simple, but I was thinking I'll just discuss in the class, but then I'm getting yeah. So this is n choose. Wait, will it? Yes, yes, we can do that. That's right. So how do we do that? So if it is n yes, you have to still do induction, but but I'm just trying to write the general term. The general term would be n choose k, and this would be x n minus 2k plus n minus 2k. But k will only go up till n by 2. Yeah. So let us just erase that and write this only. So this is yeah. So tk will come in, right? That is what we'll have to use. Yeah, but let me just write this first. So k goes from 0 to something n by 2. Um, either case, you'll get an integer maybe. You'll get a constant if it's odd. So that's fine. So then you get n choose k x to the power n minus 2k plus 1 by x to the power minus 2k. Yes. So now by induction, wait. So what were we interested in? Yeah, so it starts from 1 because let's isolate the thing that we are interested in, that is this, right? So how can we finish the question now? Yes, right? So induction is exactly the way to go. 2 cos, this is nz. That's right. And this one exactly works, right? We can actually, this will actually go, yeah, like this. And that's right. So this will be t n minus 2k and choose k and minus of this with 2 to the power, sorry, this to the power n is equal to 2 cos nz. So this is your polynomial. So it is a previous polynomials this, and so your polynomial would be, as you can understand, so this 2 cos z will become your x, right? So this is this. Yeah, nice. Mm. Yeah. It's interesting how a little bit of a manipulation changes so much. Yeah. Okay. So I think this is good. Let us see. So this is just one question that we did. So today I'm not doing new theory. Let's just practice this one question. So now I don't want to start something new. Yes, let's just do another simple check that we were doing the last day. Let's just check these simple things today. About a rotation matrix. So what is the context of this? We had seen that if you look at a function which is from C to C, okay, if you look at a function which is from C to C, which is a complex function, so you can also write it, sorry, you could also write it as this, same thing. So we had seen that if f is differentiable, then you have yeah, you have something like this. We said that this minus this, minus, you need a derivative, which is a complex number, and yeah, that multiplied with h1 comma h2, obviously divided by h1 plus I h2, this tends to 0. Limit of this as h1 h2 goes to 0 is equal to 0. This was the more or less the definition of the derivative, right? From here, we were trying to understand, if you try to view this, so this is also, f is also a function from R2 to R2. So you can try to view this thing as a matrix multiplication, right? So we wanted to have a matrix, let's say ABCD times H1, H2, right? Such that this result is f dash z. So z is fixed is equal to x comma y is equal to f dash z times h1 I2. So can we figure out a matrix from here? Can we figure out the matrix from here? So remember, f dash z is just a complex number. So can we figure out what the matrix should look like? So we want the matrix multiplication to do this very specific thing. It should mimic complex multiplication. We had roughly mentioned, but let's try to actually prove what it looks like, and then also try to understand what that matrix, what's the significance of that matrix outside this thing. Yes, so that's, but can you, yes, so yeah, that's right. So you have already guessed it. So, and you can prove it. So the point is that it's easy to prove, okay? So it will be ABB and something like this, right? Because the idea is that you put special values, you put 0, 0, you put 1, not 0, 0, you put 1, 0, you put 0, 1, and you can you can figure out what it should be. So this is how this matrix looks like. Now we're basically trying to understand what is the significance of this matrix. Why were we saying the last time that this is a rotation? It's not a rotation matrix always, but we were saying that, so that's the significance of this in this situation, right? It's a modulus. Yes, so that's already one interpretation, but that's obviously partial. What more does it encode? What does it do? So this is the modulus of the. Okay, no, that's right. But what does it matrix? So clearly you can understand that this is clearly a function from R2 to R2. Yeah. What does it do? What does this function do? What can you say about this function? I mean, you can for it. No, I didn't. No. Yes, no, but that is only for the entries. But my question is that if you input a vector to this, so right, if you input a vector to this, which means that if x comma y comes in as an input and you multiply it by this matrix, then how can you geometrically describe the output? So the output, we can obviously write what it is, x plus by minus bx plus ay, right? But what is going on geometrically, if anything significant? What is the relation between this input vector? Expansion is a yes, expansion is might be happening, right? So yes, so it is not a translation, right? Because you see, the origin goes to the origin. That is obviously not going to change, right? But yeah, you're quite there. Expansion, the word expansion has some meaning, I guess, here. So it is, but not only dilation. Why don't we take some examples? And rotation, that's right. That's right. So it is dilation and rotation, okay? So what is happening here is dilation, and that dilation is by a fixed amount. And you can obviously guess that amount is a square plus b square, the volume of the matrix. Dilation plus rotation. Obviously, when we say this, the significance of this is that a dilation is fixed. Okay, no matter what thing you input, right? The constant of dilation will be a square plus b square, because let's check it, right? What is the distance of this from the origin? It is just square the things and you can check it. So the distance you can check if you square it will be this, and or the square root of this, and the distance of the origin, meaning sorry, of the input, right, was this. So the distance gets multiplied by square root of a square plus b square always, no matter what is the input, right? So if this is some vector, then it will always get multiplied by a fixed constant, but will also get rotated. What will be that angle of rotation? Can we try to think about this? What is the angle of rotation? Then only you can say, I mean, that's one way to say that it's rotation. Otherwise, how do you prove that it is rotation? Yes, right. So its rotation should be like that, right? Should be tan inverse of b by a. Yes, so that is roughly what will happen. That's right. You can also and so from there also you can do, or you can also take the complex number approach. What is happening is that this is basically, that's where we came from. It's going to this, so you can already understand that that's what this matrix is doing, right? And so obviously you can understand that it's going to rotate by the argument of this and also expand by the modulus of that. So this is a rotation matrix. It's a very special matrix, not any arbitrary matrix. It's a special matrix. Okay. So yeah, that is just one way to view. That's why we were calling this we were calling this a rotation matrix. Okay. Yeah. So I think this was the other point. So yeah. So let's not do any new topic today. Let's conclude here today. The other join will do a bit extra next time. Okay. Yeah. Yes. Okay then. Okay. That's it for today.